Welcome to MHF4U Grade 12 Functions, Section 2.1. Today we'll be discussing how we can determine the average rate of change. So first of all, let's start with the definition. The average rate of change in a relation is the change in the quantity given by the dependent variable, otherwise known as delta y, divided by the corresponding change in the quantity represented by the independent variable, delta x, for a function y is equal to f of x. And then we have the formula for the average rate of change. So something important to remember here is that we're always looking at 2 points in the average rate of change. And we're looking at this change over a period of time. Hence why we have x1 and x2, and why we have f of x2, and why we have f of x1. So in this case, when we're subtracting here, we're subtracting the final minus the initial. Final minus the initial. And remember, when we say f at x2, all we're saying is it's the y value that corresponds to the x value that is inputted. So in this case, it's the y value that corresponds to the x2 that is inputted into the function. Okay, so with that, let's look at some examples. So there are multiple ways we can determine our average rate of change. The first way being a table of values. So in this case, they're asking us to use the data in the table of values to determine the 2-hour interval in which the bacteria population grew the fastest. So we have our time interval here, x between, or it can be x or t or whatever. In this case, they're using t. So t between 0 and 2, and delta b being given to us is 272. And delta t being given to us is 2. And that's very simple. We're just dividing delta b by delta t to give us our average rate of change for the bacteria. And the same format follows for all the other examples given to us. Pretty straightforward. And then we now know that the greatest change in the bacteria occurred during the last 2 hours when the population increased by an average of 412 bacteria per hour. Perfect. Okay. So the next way you can use for average rates of change is a graph. And something important to connect here is that when you connect the algebraic and graphical representation of the average rate of change, you can actually see that it's a secant line. So in this case, you can see that a secant line is the line that is connecting 2 points in the graph, right? And so if you think about it, this actually represents 2 different points in time. So in this case, we could actually use a graph to represent this growth on the bacteria. And on the graph, we'd always be looking at 2 points on the graph, always, always, always. So it would be the 2x values and the 2y values that correspond to these 2 points that we then use to calculate our average rate of change. So the same thing follows here. And something else that's interesting here is that you might think, well, this looks really familiar, this line looks really familiar, and you're right, because you can actually use the slope formula to calculate our average rate of change here. So that's a connection that you can form here. So let's write that down, slope. Perfect. Okay. So with that, let's look at a quick summary. So the average rate of change, as we know, is a change in the quantity represented by the dependent variable, delta y, divided by the corresponding change in the quantity represented by the independent variable, delta x, over an interval. And we have our 2 formulas here. So the first formula is the algebraic change that you can use, and you have your final value minus your initial value, and then you have that being divided by, you have that is dividing your f at those 2 points. So your function or your y values that correspond to those 2 points. And then graphically, the average rate of change will be the slope, which is what we have here. And this formula will look very familiar to you because it is the slope formula, as we know. And again, you find your delta y over delta x, and that gives you the average rate of change. Okay, so some important things you need to know. Average rate of change is expressed using the units of the 2 quantities that are related to each other. That's pretty straightforward. So a positive average rate of change would mean that the dependent variable is increasing compared to the independent variable. And so that would mean you have a positive slope. So the line is rising, the secant line is rising from left to right. Similarly, if you have a negative rate of change, that would mean then that the dependent variable is decreasing compared to the independent variable. And this would mean that your secant line is decreasing. From left to right. Okay. And then all linear relationships have a constant rate of change. So this means that your rise over run or your slope value is always the same throughout this entire function. Whereas if you have a nonlinear function, then your slope will change throughout. And so that means that if you took the average rate of change, let's say I took the average rate of change over a linear function like this, versus an average rate of change over a function like this. Well, it depends on where my 2 points are, right? my points are here, I'm going to get one kind of change. My points are here, I'm going to get a different kind of change. So that's what it's telling us. Whereas on a linear function, no matter what my 2 points I select are, I'm always going to get the same rate of change. Okay. So now let's look at some examples. So the first one is calculate the average rate of change for the function g of x is equal to 4x squared minus 5x plus 1 over each interval. So the first step for this is you're going to want to find the corresponding y values to the x values you're given. So you have x equals 2 and x equals 4. So I'm going to put in this case, so in this case I'm going to put in my formula g of x, and I'm going to take g of 2, which gives us 7, g of 4, which gives us 45, and then now I have the corresponding y values to my x values that were given to me initially. And I can calculate the average rate of change. So I subtract final minus initial, always, and this is what gives us the final average rate of change. Okay, so now for question 2. We have an emergency flare that is shot into the air. Its height in meters above the ground at various times in its flight is given in the following table. So for part A, they're asking for the average rate of change during each interval. So this is really straightforward. I just used the same method that we had before, and I calculate the delta y over delta x using the table. So, I look for 1, I knew that was my x, and then I found the y that corresponded, looked at 2, found the y, 3, same thing, 4, same thing, and then subtracted and divided by each other, and I got these two values. And then for B, we're looking at what these results mean. So we can see that means that in the first interval, the height is decreasing at a rate of 15 meters per second, and for the second interval, the height is decreasing at a rate of 5 meters per second. And that means that overall, this entire thing is decreasing 3 times on average. Okay, then for question 3, it says, given the functions f of x and g of x shown on the graph, discuss how the average rates of change, delta y and delta x, differ in each relationship. Okay, so this is actually what I was talking about before, right? Because you can see here that this function is linear and this function is nonlinear. And so that means that depending on where I select my points for my average rate of change on the nonlinear function, the resulting slope is going to differ. Whereas for my linear function, no matter where I select the points, it will always give me the same slope. And so that's what we get in our answer. We see that f of x is increasing at a constant rate, right? Like the slope will always be the same, it's always going to increase at the same rate. Whereas for g of x, it's decreasing on negative infinity comma 0 and increasing on 0 comma infinity, which we see here. So basically, the x values are always increasing this way, but the x values are always decreasing that way. So that's what we see here with our two functions, and as a result, the rates of change would be different, which we can draw. So let's say I took like these 2 points here, I'm seeing that's always going to give me a positive rate of change, whereas here, if I took points on this side, it would give me a negative rate of change. Perfect. Okay, so in this video we talked about the definition of the average rate of change. We looked at some examples using a table of values, using a graph, and then a summary of the main points. We talked about how the average rate of change is equivalent to the slope graphically, and then we looked at some examples again. And that's it for this video. Thanks for watching. I hope you enjoyed. As always, if you have any questions, feel free to contact our tutors on passionateminds.com, our website. And thank you.